Hey guys, so I'm going to be doing a solution video of essentially all of the Div 2 problems from the recent round 664, and well, I didn't do a screencast because I wanted to focus on the round and it was a Div 1, but I'm going to go over some of the solutions now. So this is Div 2A, and the problem is as follows. You're given a certain amount of balls of different colors, specifically red, green, blue, and white. Let's take the sample of 8. I'm not going to use different colors. It's not that big a deal. So 8, 1, 9, and 3. Then what you want to do is you want to arrange these balls to make a palindrome. For example, say you had 2 red balls, 2 green balls, 1 blue ball, and no white balls. Then you'd be able to make a palindrome like this, for example. And if you also had a white ball, which I'm going to use black since this is a white background, like you wouldn't be able to make a palindrome. It wouldn't be possible with that many. So the way to check if it's possible to make a palindrome given only the counts of each elements is essentially this. Either all of the numbers have to be even, or everything even except for 1. So let's go over what happens in both of these. Let's say all of them are even. Like for example, you have 2 quote-unquote white balls, 2 red balls, and 2 green balls. Then if you consider a line that splits the palindrome down in the middle, you can essentially put one of the balls on this side and the other of the balls on this side, and it will still be a palindrome because it'll be symmetrical. But this has to have an even number of balls for that to happen. So if all are even, you can construct it this way. So now we can check what happens if all of them are even except for 1. So if there's an odd number of one color of balls, for example, there are 3 red balls, we can place essentially the odd one out in the middle. And then we can do the same thing with the kind of divider line where we, for each ball we have of one color, we put the same color on the opposite side and it will still be a palindrome. But if we have more than one that's odd, then we can't do the same thing because this won't be a palindrome. And like there's no possible way to do it if there's more than one odd. Because every ball in the palindrome must be matched with another one, except possibly the one in the center. And if there are more than one balls that don't have a match, then because only one ball can be in the center, it's not possible. So, in a sense, this is why these conditions are necessary to be a palindrome. So now what we can do is, we can do some operations on these balls. We can say, well, what we can do is, we could subtract, the operation we can do is we can subtract 1 from red, green, and blue, and then add 3 to white. This is only possible if you have at least one of all of these. And then after this, you want to check if it's, and then you can do as many of these operations as you want until you get a certain configuration of balls that you can make a palindrome out of. So either you check if you can initially make a palindrome out of all of the balls, or you check if you can do some number of operations and then see if it's possible to arrange them in a palindrome. Now, the crucial observation for making this implementation nice is you only care about the parity of all of the balls. And because each operation, actually, why am I erasing these? Each operation changes the parity of all of the balls. And then if you do it twice, it will change the parities back to what they were originally. Because this will be, for example, -2, so it won't change the parity at all. This will also be -2, this will also be -2, and this will be +6. So it's only worth doing an operation 0 times or 1 time. Therefore, you only have to check those cases in the implementation. 0 or 1 operations. Yeah, that is it for A. You just check all of that. Let's go into B now. So in B, you're given wait, does it not let me copy that? Okay. So in B, you're given a chessboard. I'm going to make it very sloppily because we're just going for speed here. Jeez, this is quite bad. Alright. So it keeps drawing these tiny things. So I can't click off. This is the wonders of MS Paint. So we're given a chessboard. Hopefully it doesn't look as bad as this. Actually, we can use this as an example. And we're also given a rook, which I'm just going to make a red blob, that we want to move around the chessboard. So a rook can essentially move, it can move in any direction as long as it's in a straight line, like vertical or horizontal. So a rook in this position can move to any of these squares because they're all vertically or horizontally aligned. And what you want to do is you're given the size of the board and the initial starting position of the rook, and you want to create a path for the rook that will visit all squares exactly once. Yeah. So I'm going to use numbers to represent the time at which you visit something. So for example, you would start here, visit this at time 1, then go here, visit this at time 2, and go here, for example, and visit this at time 3. Note that you're allowed to jump over cells that you've already visited. So for example, here you can go through the one cell, you just can't stop there, because that would count as visiting it again, which is not allowed. So you want to create a path for this rook that visits all cells exactly once. And it's always possible to do it. So you just need to print the cells in the order that you visit them. So there's a relatively simple construction to this, where essentially wherever you're at, you just keep going right. So you go to 1, then you go right to 2, then you go right to 3. And then once you're at the right, then you just keep going left whenever it's possible. So you try going here, but you've already visited here, so don't go there. You try going here, you've already visited here, so don't go there. You try going here, this is unvisited, so you go here. And then if there was another square, for example, to the left of this, you would just keep going and whatnot until you reach the end. But now we're at the end, so now we have to go to a different row since we visited this whole row. So let's just go to the first one. Then the same thing. We can do the same exact implementation. We just keep going right until we can't anymore. Then we have to find another row, so let's just find a row that we haven't visited before. Now we'll go here. Then we just keep going right until we can't anymore, and already we can't anymore. So let's go left until we can't anymore. So 10, 11, and 12. So essentially, it doesn't matter where you end up because you can always do this strategy of going right and then left, and that will let you visit an entire row. So you just have to do entire rows at once, and then it will let you visit all squares. Yeah, there are many other possible strategies for B, but this one I see as relatively simple to implement, so it should be good. Let's move on to C. Okay, so you're given 2 arrays. Let's use the sample. So 2640, and 24. All elements are, so what's important here are the constraints. N and M, the length of the two arrays, are less than or equal to 200. And AI, the elements of the array, are less than 2 to the 9th, which is small, that's equal to 512. So 2 to the 9th, let's say we had a complexity, I would say like O of 2 to the 9th times NM. That would be okay, because it's just, do some quick maths. Yeah, it's just 20 million. So that will definitely pass in time. So we can kind of like, already we see that the constraints are really small, so we can try some sort of brute force approach. And indeed, that's what we can do. Let's just, we're trying to, and all this is before even reading the problem, essentially. So what we need to do is, for each value of I, we need to pick some j. We need to pick some j. These j's can be whatever they want. You can pick the same value of j for different values of I. And what you're going to do is, once you pick this j, you're going to append the value ai and the bitwise and of aj. And then you're going to append this to a sequence. Then you're going to do this for all values of I. Let's say I do this, then the bitwise and is also 2. Then I do this, then the bitwise and is 4. Then whatever I do, the bitwise and for this is 0. Then you're going to take the bitwise OR of all values in this sequence, and then that's going to be your answer. So you want to minimize this value. You don't need to print the actual indices, you just need to print the minimum possible value. So first I can go over the bitwise notations. If we write out each number as a bit mask, let's say 2 is 0, 1, 0, so just 2 is 0, 1, 0, 6 is 1, 1, 0, 4 is 1, 0, 0, 0 is 0, 0, 0, again 2 is 0, 1, 0, and 4 is 1, 0, 0. So a bitwise AND of two numbers is, for example, 0, 1, 0 and 1, 1, 0, is you keep all of the bits that are set in both of them. So this one has 0 and 0, which means it's not set in either of them. This one is 1 and 1, which is perfect. That's exactly what we need. And this one is 0 and 1, which means it's set in this number, but not in this one. So therefore, we can't take it. So our final resulting bitwise AND is 2. And in terms of bitwise OR, we do the same thing, except we take all values that are set in at least one of them. So in this example, this 0 is set in neither of them, so it would be 0. This 1 is set in both of them, so we can take it. And this 1 is set in this one. And so because it's set in at least one, it doesn't matter that this one isn't set, we'll still take it. So that's bitwise AND and bitwise OR. Now what we're going to do is try all possible answers. This will be, there are only 2 to the 9th possible answers because the numbers are small. So let's write out the strategy. Try all. What is going on? Sensitivity got screwed up or something. That is annoying. Okay, so I'm gonna get rid of that because that looks terrible. Okay, so let's say we're trying 5, for example. 5 is 101. I don't know what happened. Why did this get screwed up? This feels kind of weird. I guess we're gonna deal with that. So let's say we want 5 as an answer. Now, it's sufficient to check that all of the numbers in the new sequence we create are essentially submasks of this. So what we want is, we don't want any of the zeros to be set. Because if a 0 is set in any one of the numbers in the new sequence we create, because our operation is bitwise OR, we're going to have that in the answer. But since we're trying to minimize it, we don't want this 0 to be set. However, it's okay if some of these 1s aren't set, because that means the mask is just going to be smaller, and that means we'll, like for example, let's say the final mask we get is actually 4, which is 1, 0, 0. Then when we're trying out 4, well, we'll get that, and so it doesn't matter that we don't actually have 5 because we have a smaller number, so that's better for us. So essentially all we need to check is that we can have a configuration that doesn't set any of the zeros. So how do we do that? Well, we can try each value of I, and then we can try each value of j, and for each I, we just need to find any j such that the bitwise AND doesn't have any of the zeros set. So for example, in 2 and 2 equals 0, 1, 0. So that's bad because this 0 would be set if we had that. However, 2 and 4 is equal to 0, so that's perfect. So we would match 2 with 4. Then for 6, we would also take 4, 1, 1, 0, and 1, 0, 0 equals 1, 0, 0, which is 4, which is also fine because this bit is set in 5. So we'll take this. 4 and 4 is 4. 4 and 2 is also 0, but neither of that matters. Like, both of them work. And 0 and anything is 0, so we'll just match those. So essentially we can match everything to 4. And, well, that's fine. So now we verified that 5 is possible because there's a configuration that doesn't have any of these bits set. However, let's say we wanted something like 1. This would not be possible because 1 equals 0, 0, 1. For example, for 6, which is 1, 1, 0, either we have to AND it with 1, 0, 0 or 0, 1, 0, and either way, we're going to get something that sets one of these zeros to 1. So 1 would not be possible because the condition is not satisfied. So we just need to, we can essentially try all possible answers and then verify if it's possible. And so there are 2 to the 9th possible answers, and O of nm, it takes O of nm time to verify. So this is totally fine. As I said, it doesn't use that many operations. There are more efficient ways to compute the answer, like doing some sort of like greedy on the highest bit, but that's not very important for these constraints. I think the editorial code tells you how to do that, so if you want to see that or work it out for yourself, that's a nice extension of this problem. But anyway, let's move on. So now we're heading into the div 1 problems. Yeah, this one is fun. So this is 1A and 2D. So let's just sanity check again. Okay. Yep. So here's how this problem works. We're given an array. We're given an array. I'll just kind of copy in the sample. We're given 3 values, n, d, and m. And we're given an array of also values, 8, 10, 15, 23, 5. Now, the way this works is, trying to figure out a way to, I guess I can just explain the problem in the context that it's given. So you have a chat group, and each day you're going to make fun of the main character with a fun factor of this value. And so essentially, if this value, if the fun factor you have is higher than the value, what is it? Is higher than the value m, so if this is higher than m, then you're going to be muted or muzzled for d days. So for example, let's say we do it in this order. So here you'll start here. 8 is less than 11, so that's fine. You can use 8. Then 10 is less than 11, so the same thing. So 15 is greater than 11, so that means you're going to be muted for these 2 days, and then we're at the end. Then the total, the total fun factor is the sum of the fun factors on the days which you actually speak. So this would be 8 plus 10 plus 15 equals 33 for this. So you want to find any sort of ordering where you can say swap. You can swap the elements in any order you want, so that, does it say they're unique? Doesn't really matter. But you want to find any ordering that maximizes the total fun factor you have. So, for example, in the sample, the best ordering is, let's just write it out, 15, 5, 8, 10, 23. 10, 23. So here you would go here, get the 15, be muted for 2 days, then you'll get 10, not be muted for this, and then you'll get the 23 and you'll be muted after, but it doesn't matter because you're at the end. So the total benefit is 48, which is much better than the 33 we initially had. So you, as the answer, you don't have to print the ordering, but you do have to print the best total fun factor you can get. So let's think about what the final sequence is going to look like. We can see from the sample straight away that it's okay if we have one of the elements that are greater than m at the end, because this muting is going to be at the end, so it's not going to matter that we get muted here, since it won't affect any later ones. So that's kind of something useful we can do. And then, so now we can kind of also relabel our sequence. So let's say an element is bad if it will cause us to get muted. Let's say an element is bad if it's strictly greater than m. So for example, this is bad. This is a good element because it won't get us muted. This is also a good element. This is also a good element. And this is a bad element. So now, there are many different strategies that you can try for this problem, and there are also many different strategies that will be wrong for this problem. One of the strategies that does work is essentially fix the number of times you get muted. Fix the number of mutes. Then, so that's fine. How would you do that? So essentially, you want the ones that get you muted to be the highest. Because if they're lower, then you can swap them with a higher one and it won't change anything. Or it'll be strictly better. So that's fine. And then you want the ones, you want the values that you don't get because of being muted to be lowest. Because those are the ones you don't get, which means the ones you do get are higher. So there are a couple of conditions like this. Once you get this kind of idea, it just becomes a casework problem essentially. So there are a few cases. One, so first of all, the number of times you actually get muted is fixed, but the number of elements like, for example, the number of X's that I would draw, the number of elements that don't get counted because of mutes, you can use a formula for it. So you're going to stick you can assume you're going to stick one of the bad elements at the end, and then all the rest of the bad elements are going to last d days. So it's essentially, let's call mu the number of mutes. No, let's just say u for the number of mutes, and then it's u minus 1 because you subtract one of the mutes because you can put it on the end, and then times d. That's the number of elements that are going to not count because of the muting. So if this is greater than n, then there's no possible way to do this. And also, if it's greater than n minus u, then it's also not possible because, like, the u elements are being used to be muting. So all of the rest are either good or they're in a position that's muted. So of those remaining elements, there are n minus u of them. So if you have more than those, then you're kind of muting too many things, so it's not possible. You're muting more elements than there are in the array, so it's not possible to do that. And actually, I think that's the only condition. Let me check my code to verify this because don't want to lead you astray. So here, oh yeah, and also obviously like u has to be less than or equal to the number of bad, because if you have more than that, like, you can't mute for a good one, so it just won't be possible. And then yeah. So now, once you check that it's possible, now you just need to get the best way to configure the array for the number of mutes. So first of all, you get the best you you automatically get u of the bad elements. So you can just say you're going to get the highest ones there. Then of the elements that are muted, first of all of the rest of the bad ones have to be muted. And then yeah, all of the rest of the bad ones have to be muted. And then actually, it isn't necessarily true. What you can say is, if a bad one isn't muted, but you're also not counting it to be muting something, you can just ignore it. And that makes implementation easier because even if that's like not entirely accurate and it's undershooting the answer, later on, when you try a different value of mutes, that will take that into account. So essentially, even if it's inaccurate now, later on when those bad elements are actually used to mute something, it'll make up for that. It will be accurate in the future. So you don't have to check that it's accurate now, and that kind of makes implementation easier. So essentially what I mean is, here I don't say, you could theoretically check if you're not muting all bad elements, then it's not possible, but that's a bit tricky because at the same time, this is the This is the minimum number of elements that you'll end up muting. But you don't actually have to place this one on the edge. You can put it, you don't have to place the last bad one on the edge. You can move it, for example, here, and then you'll get a few more mutes out of it. So you can check that condition again, but it's not necessary. So then essentially the way to check this in O of 1 is to use prefix sums. First of all, group all of the bad ones and the good ones together in descending order. So the biggest ones are first. So these are the bad ones and these are the good ones. Then you can create prefix sums of those, which is basically like each prefix sum is the sum of all elements before it. So the prefix sum here is just 10. The prefix sum here is 8 plus 10, and the prefix sum here is 5 plus 8 plus 10. So I will write those out. So the prefix sum here would be 23. Prefix sum here would be 38. Then this would be 10, 18, and 23. Now this is nice because it lets you get the sum of the first I elements, essentially in O of 1. And like this prefix sum, the prefix sum of these three elements is the prefix sum of this element plus the prefix sum of these two elements. And similarly, if we add another element, say 3 here, then the prefix sum of 3, prefix sum of the first 4 elements is the prefix sum of the first 3 elements plus this element. So you can also compute the prefix sums at the beginning in O of n and then use them later. So now that we group these together, well, first we're going to get the first U bad one. So if U is 1, we're going to get the 23. If U is 2, we're going to get both of them. And then we're going to assume that we mute the remaining number of bad ones. But sometimes we mute more things than is possible. So, like let's say we get this, and then we have to mute 2 more in some scenario. So we can mute this one because we have to mute the bad ones first. And then, but we also have to mute something else. So essentially we only have to mute the lowest one, because if we were to mute a higher one, then we could, like, it's worse than muting the lower one, because then we would miss out on the higher one. So the strategy is to first mute all of the bad ones, and then mute as few of the good ones as possible, and at the same time mute the lowest good ones. So with our prefix sum representation, this is nice because we're removing some suffix of the good ones, which means we only need the sum of the remaining prefix. So in the code, it turns out to be very simple. You just compute the suffix you need, or you compute the prefix you need, and then because you have the prefix sums, you just add it. So it's kind of a messy thing with indexing. The implementation is slightly annoying, but it's also good to work out on your own if like all of this isn't clear, because there's some parts like indexing, for example, like not making off by 1 errors and computing everything right, that these types of problems just create, and I guess it's good to have practice on those. So yeah, that's basically all I have for this problem. Now we're going to move into E. E is fun. I like this one. 2E/1B. This is the last problem I solved in the actual contest. So you're given a graph. Let's say it's like this. I'll just use their example because they have nice images already. Actually, I'm gonna make it slightly bigger. Boom, boom. Then we create an edge here. Create an edge here. Create an edge here. Create an edge here. And here. And here. And then these edges are weighted, so we'll give them all a weight. 4, 5, 6, 2, and 3. And it's a constraint that all of the weights are distinct. Now, the constraints are very important to notice for this problem. The first constraint is that the out degree of each node is at most k. So let's say, like any vertex can only have at most k edges outgoing from it. So if k equals 3, then we can't have an edge with 4 outgoing edges because that would be greater than k. So that's not possible. Another constraint that's important to notice is that k is small. K is 9. So this is an important constraint. Like, small things are good to focus on. So let's just write that out. K is less than or equal to 9. Underline it a couple times for good measure. And let's go through this. So what we need to do is we need to create some sort of tuple, which is just a list of integers. We need to create a tuple of length k, where each value is ci, and I think they call it c, right? Yeah. Then, so the first constraint is that each value must be less than or equal to I, like its position in the tuple. So this is position 1, this is position 2, this is position 3. So this value can be at most 1, this value can be at most 2, and this value can be at most 3. I'm going to use a different color for that. 1, 2, 3. So now, what does this tuple do? Well, it's kind of weird, actually. What it does is, it's going to say, so at position 1, the value is 1. So it means of all vertices that have an out degree of 1, for example, this one. This vertex has an out degree of 1 because it only has one edge coming out from it. And so does this one, and so does this one. However, this vertex has an out degree of 3 because it has 3 edges coming out from it. So what we're going to do is we're going to write out all of the outgoing edges to each vertex in sorted order. So for example, this is 1, 4, 5. I'm just going to write the weights out. You can assume it also comes with the vertex that it goes to. So this edge with weight 1 would go to this vertex, this edge with weight 4 would go to this, and this edge with weight 5 would go to this. Now this one, the rest of them only have one outgoing edge, so this is easy. 6, 2, and 3. And so essentially, if the third position has value 3, that means for any node with 3 outgoing edges, we're going to essentially activate the third edge in the sorted position, or the sorted list of outgoing edges. So we're going to activate this edge. Just gonna draw over it. And then the rest of these edges, actually, yeah. So we're going to activate this edge, and the rest of the edges are going to be deactivated. Okay, and for vertices with, so for example, if this was, although actually that would be wrong, because this value is 1, so we would activate the first edge, and the rest would be deactivated. So if this was 3, then we would activate the third edge and deactivate the other 2. And of course, if it was 2, we would do the same thing, but for this edge. So that's what this tuple means. Let's call a tuple valid if, so for example, I'll deactivate these. Let's call a tuple valid if you can start at any vertex, follow the edges that are activated, and then eventually get back to this vertex. So for example, here we can go through this edge, go through here, go through this edge, go through here, go through this edge, go through here, and then go through this edge and end up back. And well, we can do that for any vertex. Like, we can just follow the same path and eventually get back to it. However, if we actually had the tuple 1, 1, 1, then we would deactivate these two. Now let's say we start here. I'm running out of colors. So we can use this, then we can go to this edge, come out here, go to this edge, and end up back here. Now that's fine, but what about other vertices? We can go here, then we can go through this edge to here, then through this edge to here, and then there's no way we can get back, because the only edge that leads to it is gone. So this would not be a valid tuple, because for all vertices we can't get back to it eventually. And we want to count the number of valid tuples. Now again, let me reiterate. K is less than or equal to 9. So because all Ci is less than or equal to I, for example, C1 is less than or equal to 1, so it has one possibility. C2 is less than or equal to 2, so it has two possibilities. In total, we have 1 times 2 times 3 times 4 times ... times k possibilities for the tuple, which is conveniently equal to k factorial. So 9 factorial is a small thing. It's factorial. It's 362,000. That's very small. So we can, if we can find a smart way to like brute force all of the possible tuples we can make, then we'll be done. It'll be easy. How do we do that though? Because k factorial times n, what color did I use? K factorial times n is way too big. Because n is, of course, 2 times 10 to the 5th, classic large constraints. So there's something better we have to be able to do. And indeed there is. So, first of all, let's refine our check for whether an edge is valid or not. Or whether a tuple is valid or not. What it means to say that we can get through any node. Okay, first of all, note that with this construction, every edge is going to have exactly one outgoing edge. Or every vertex is going to have one outgoing edge. So because there are n vertices, there are going to be n edges remaining in the graph, at most. And if we have some weird graph where, for example, like one edge doesn't have any outgoing edges, then it's never going to be possible because we can't even leave this vertex no matter what we do. So first it's a special case if any vertex has 0 outgoing edges, and we should print that there are no valid tuples in that case. That's important. I think that got a lot of people in the contest, that special case. So don't fall for that, notice it, and then once you do that, now we assume that every vertex has at least one outgoing edge, and therefore, in the tuple it has exactly one, so there are n edges. And we want the graph to form a big cycle, because otherwise it wouldn't be possible for at least one vertex to get back to it. Like, for example, if we did this, if we remove these two, this wouldn't be a cycle because like this edge isn't part of the cycle. But if we remove this and this, then this edge, all of the edges are part of a big cycle. So how are we going to do this? So we can again reframe our condition. And what we can say is every edge, well, so we already know every edge must have at least one outgoing edge. Every vertex must have exactly one outgoing edge. We can also say that every vertex has to have exactly one incoming edge. Because let's say it didn't. Let's say, for example, there were 3 vertices, we had an edge here, and then both of these edges fed into this, both of these vertices fed into this vertex. So this vertex has an integer of 2, this one has an integer of 1, and this one has an integer of 0. So if any vertex has an integer of 0, then even if we leave it, there's no way we can come back to it. But it's the same as saying every vertex must have an integer of exactly 1. because if any vertex has an in-degree of greater than 1, well, we by definition, all of the in-degrees sum to n. So 1 plus 1 plus 1 equals n. However, if we have something that's 2, then that removes the possibility of a different one being 1. For example, if we have 2, then we try and make more numbers that sum to n, we just can't. If n is 3, then this has to be 0, and therefore it's impossible. So the math ends up checking out here, and we can and it's true that each vertex has to have an in-degree of exactly 1. So now we've reframed our problem many times, and we're going to do it again. Now, we can kind of scrap the whole edge weight thing. Instead, what we'll do is we'll replace each edge weight with its position in the sorted list of edges, like from the vertex that it goes out from. So this is position 1, so that's fine. This is position 2, so it's 2. This is position 3 in this vertex's sorted list. And all the rest of these are position 1. So now all of these edges are these 3 edges are kind of in the same group. That is, if we make this tuple value 1, all of these edges are going to be taken, and otherwise all of these edges won't be taken. So all of the edges with a red arrow pointing to them are kind of like connected. Either you take all of them or you take none of them. Meanwhile, these edges are disconnected because while this is also position 1, it's a different value of out degree. So it would be a different value in the tuple that influences it. So this one, let's say, gets a green arrow, this one gets a light blue arrow, and this one gets a purple arrow because they're all different. Now let's say this. Let's say, here's where the magic comes. I need to find a color. Let's look at this vertex. Right? So for this vertex, if we take both an edge with a green arrow, drawing arrows to arrows, and edges with red arrows, then this vertex is going to have in-degree 2. So what this means is, if we take red, we can't take green. And the same goes for this vertex. If we take light blue, then we can't take red, and if we take red, we can't take light blue. So we can use the vertex, the edges that feed into each vertex to create kind of a system of constraints. Like, so red can't be the same as green, and light blue can't be the same as red, just from looking at these 2 vertices. The other vertices don't give us any such constraints, so that's it. A valid tuple can't take both a red edge and a green edge, and a valid tuple can't take both a light blue edge and a red edge. It must take exactly one of these 2. However, that's easier to check because essentially, if we don't take exactly one of these 2, then we'll end up having some other conflict. Like if we have a vertex, if we don't take exactly one of these 2, if we don't take exactly one of these 2, that means like this vertex has in-degree 0. That means that some other vertex, for example, this one, will have in-degree greater than 0. So that's essentially fine. Yeah, this vertex will have to have in-degree greater than 0, because again, all of the in-degrees must sum to n. So if we have 0 plus 1 plus question mark, equals n, let's say n equals 3 for this case, then the question mark will have to be 2 and it'll be greater than 1. So we'll eventually find it because it'll break one of these conditions if it's greater than 2. So we don't have to worry if we don't take any edge because that will be accounted for. So that makes implementation easier. So now that's kind of it, actually. Because once we try a tuple, because when let's say we're trying all possible tuples, then yeah, let's say we're trying all possible tuples, and then what we're going to do is we can check for each value. Like, for example, this one gets a red edge. There are no vertices with degree 2, so we'll just ignore this. Anything's possible for it. And if this was 1, then this would get a green edge. So we would just check for all of these if there's any condition that says we can't have both of these. And if so, the whole tuple is invalid. So once we try all possible tuples, which is again only k factorial, so we can do, we only have to check if it's impossible between each pair of things in the tuple, which is k squared to do if we pre-compute all of this. So the final complexity is k factorial times k squared. Now this is great, because that's kind of it. But there are a few more details of implementation we need to take care of first. First of all, like, I've been drawing in colors this entire time. We can't use arrays that have colors as indices. That's stupid. So how do we like turn these colors into numbers? Well, there's a simple thing we can do. We can say this is an edge of index 1 that comes from a vertex without degree 3. And this is an edge with index 2, which comes from a vertex without degree 3, and this is 3 and 3. And the rest of these edges, the red ones, are index 1 out degree 1. So we can essentially create like a 4D array that says basically if an index from this element, if a vertex in this position, like position 1, then out degree 1, and then we would map it to some other vertices. You can also compress it into a single integer by just multiplying one of them by k. That's not really necessary, so I'm not going to describe how to do it, but anyway, so you can create this transition matrix. Another thing is that we can possibly have like a vertex's in degree could be a lot. Like, it could be too much to just do n squared. So what we can say is it's only necessary to keep at most 2 of each colored edge, because like all we're doing is we're saying for each edge that feeds into this vertex, like, we can't have both a green edge and a red edge. So we're just using the edges that go into a vertex to create the conditions. So it doesn't really matter how many of each edge we have. Like, if we have 5 green edges, it's going to be the same as if we only have 1 green edge. However, there's also one other important thing about this, that if we have 5 green edges, that means we can't take green edges at all. Because let's say we have some magical green edge that comes from somewhere, and it's green. That means if we take a green edge, by default we'll have 2 bad ones. So we'll actually say that green can't be with green, and therefore we can't take green at all. So this tuple, in this case, wouldn't be valid because we can't take green at all since it contradicts itself. So, yeah, that I'm very glad for sample 3 because that actually caught that case, and I probably would have taken a long time to find it otherwise. So Props to the setters for that. Thank you for saving my rating, I guess. And yeah, so in summary, we can try all possible tuples efficiently. 9 factorial times 81 is 29 million, which is also very small. In terms of constant factor, it's not the best. And you can do any kind of method you want. Like you can use I use the DFS to enumerate all possible tuples. Like for example, where am I? I use the DFS here, and use the DFS for the distance, and then for each like possible thing of the distance, you just extend it and then continue on. There are other ways you can do it too, like a BFS manner or just whatever you want, really. Whatever you can find that makes it work. So yeah, brute force, create the conditions, and that's basically it. This whole thing is a glorified brute force problem, and it's kind of nice because it takes a lot to reduce it to that. Alright, let's move on to F, the final problem that I think only one person solved officially. Yeah, one person solved this. The other person failed system test somehow. So, although this is in Div 2, of course, more people solve this in Div 1. So, we're going to 2F, or 1C. I did not solve this problem myself. I found the solution and then couldn't implement it because I don't have a good library. So let's do this. You're given... Actually, let's just go over some definitions. So a BN string is a string with just B's and N's. Like it's just those characters. And they're usually not drawn out in terrible handwriting. So, yeah. And you can do some stuff to a BN string. You could, for example, remove a character. You can remove a substring of NB. You can remove a substring of BN. You cannot remove substrings of NN or BB. You can't do that. Only NB and BN, because that's how the problem works. You can add a character at the end, either B or N, or you could add a string BN or NB to the end. Yeah. What was that? Okay. So that's what you can do. And let's say you're given another BN string. Let's say BB, BNN. And you want to do some operations to make these strings similar. What does it mean to be similar? Well, they give a definition in the problem, and essentially what it means is if you sort the strings, they'll be the same. So for example, these strings have different lengths, so it's obviously not possible for them to be the same. But if we say stuck BBNNBB, then this would be BBBNNN, and this would be BBBBNN. So this wouldn't be the same. However, if we made this BBNNBN, then we would have 3 B's and 3 N's. And here, at the same time, we'd have 3 B's and 3 N's. So in terms of strings being similar, all we care about is the number of B's and the number of N's having to be the same. Now that's a start. There's and there's also something else cool that we can do. So let's say we have... What we want to do is we kind of want to get rid of the string part. Like, let's say, for example, so the first operation, remove a character of S, doesn't depend on the order of the characters at all. Adding a character to the end, and similarly adding a string also doesn't depend on the orders at all. Like, it doesn't matter what's over here, because we're just going to stick something else on. So the only operation that could potentially depend on the order is removing a substring bn or nb. However, it turns out that this doesn't either, because if we have both an n and a b in a string, then there's got to be some barrier position where they touch, because otherwise, like, it would only be one character. And therefore, at this barrier position, you're either going to have a substring of bn or nb, no matter where the characters are. So as long as you have at least one n and at least one b, there's always going to be at least one substring of bn or nb that you can remove. So in fact, order doesn't matter at all for the operations, and order doesn't matter at all for similarity. So we can in fact reduce this to just, we can reduce the entire problem to just number of b's and number of n's. So for example, both of these have 3 b's, 3 n's. Yeah. So that's the first observation. So now, like, we're totally done with the string part. So for those of you who hate strings like me, rejoice, because this is not a string problem. So now let's get into what they're actually asking us about. Now that we've kind of reduced the statement a bit, we want to find a new string. We want to find a new string that, wrong tab. We want to find a new string. Sorry, we're given a list of strings. Like, these are the inputs, for example, a list of bn strings. And let's, for example, take this as an input. So b n bn. So this is 1b 0n. Just gonna write this out. So this is 0 1, and this is 1 1. And we want to find a new string. Let's just also use the tuple notation. So x, y, such that the distance, that is the number of operations you need to take to, actually, let's just say the distance between two strings, for example this, is the number of operations you need to make them similar. And remember, similar means that the number of b's and the number of n's are the same. And that's the only condition for being similar. So, yeah. And we want to make it so we want to find some string such that the maximum distance to any of the given strings, so let's say, for example, we take 2, 3. Then the distance here is 3, distance here is 2, distance here is also 2. So the maximum distance here would be 3, and we want to minimize the maximum distance to any of the strings. Maximum is important. It's not the sum. It is strictly the maximum out of all of them. Yeah, so then we have to print this maximum distance and also the string we get. So it's kind of constructive as well. And how do we do this? So there's a crazy idea you can get, and it's to binary search on the maximum distance. Now let's say we, for example, first, is it even possible to binary search? Well, yes, because like if you can get all of the distances to be at most, like if all the distances are less than or equal to k, then obviously all the distances are less than or equal to k plus 1. And similarly, if some distance is greater than k, then it's also greater than k minus 1. So then there's like some point where it's not possible to do things these small, and then there's a magic point where now it's possible to do these, and we want to find this point, so we'll do some classic binary search stuff. Okay. Cool. How do we do that? So now we have a fixed distance. Let's say we're searching for a distance 3. So there are similar problems in the 1D version. Like let's say you had 3 points, 1, 3, and 4. And we wanted to find some points such that the maximum distance between, we wanted to find some x such that the maximum of like x minus 1 and x minus 3 and x minus 4. The maximums of all of these are absolute values, which means just the distance. The maximum of these distances is, for example, 3. So the way we would solve this is, for a fixed distance, we could say that each value creates an interval of points that are possible. So for example, for it to be of distance 3 from 1, it can be any number within the range of, this should be inclusive, -2 to 4. For it to be 3, it would be any number within the range of 0 to 6. And for it to be 4, it will be any number within the range of 4 to 7. Wait, no, sorry. Any number within the range of 1 to 7. Then we would find the intersection of these intervals. So for example, -2, 4, 0, 6, and 1 and 7. Then the intersection would be these, the interval. So this is -2. Wait. This is -2. This is 0. This is 1. This is 4. This is 6. This is 7. And all of these are intervals on their own. It's very messy. But the intersection will be the interval 1 to 4. Then any value on this interval will be an answer. And we can just take any of them. Now this is the 1D version. The 2D version, because we have a more complicated distance function, is a bit harder. But this is the general idea that we're going to use. So in a 2D world, instead of forming a line, it's going to form a shape. And let's think about the shape that it actually forms. So for example, we have the distance x equals 3. So now we're going to draw a coordinate plane. Because we need to draw out the shape. So this is 0. This is x equals, this is 1, 2, 3, and whatnot. I'm going to use orange, actually red. So now let's say we have the tuple, I don't know, 4, 7. Right, now let's say we had this to be 1. So we have 1b, actually wait, this is 3. So we have b, 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 sorry for my handwriting, it gets worse with every letter apparently. B, 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 N, N, and N. Now let's say we fix it so we have 1B, right? So this is a change of -3. So like this is equivalent to -3 and then question mark because we don't know yet. So 1 and then what? So let's say we had 0, right? So then we'd have b. And then we could stick 3 of these bn's on, and then we would get exactly this, because of the operation allows us to do that. So for 1, we can have 0, which is also a delta of -3 -3 relative to this one. Let's say we had 1, 1, which is -3 -2. Then we would have this string. Then we could stick 2 of these bn's on, and then we could stick another b on to make it so we would get 1, 1, then 2, 2, then 3, 3, then another b for 4, 3. So it would also be 3 operations, which is fine. And it turns out this will work for 1-2 and 1-3 as well. However, once we get to 1-4, like this one we have to increase by 3, and this one we have to decrease by 1. So it's actually going to take us at least 4 operations to do this. But because we have to have at most 3, that's not possible. And if we went to -1, then these would be 4 apart, so there's no way we can do that in 3 operations. So, yeah, so the range is from 1 to 0, 3. And therefore, in relative terms, it's 4 minus 3 to 3 minus 3 to 0. So we'll get rid of these and start drawing on the plane. So this point works, this point works, this point works, and this point works, and that's it. So now, let's fix it. Let's fix the delta to be -2 question mark. Like this is closer to 4 than the other one was. So all of these points that worked before also have to work here. And like 2, 0 has to work because it worked when it was 1. So we can increase this by 2, increase this by 3, and yeah. 2, 1 also has to work. 2, 2 also has to work. 2, 3 also has to work. And now 2, 4 also works because here this is 2 below, and this is the distance of 1, so the total distance is 3. But because this is 1 closer, what didn't used to work before now works because we can spare that extra operation to make this lower, or to make this higher. So now we will also draw this point. And 2, 5 doesn't work because it's 2 apart and 2 apart, so it takes 4 in total. So now we have an extra point here. And you can kind of sense a pattern going on that, like when we move to 1, it's going to behave the same way. Or wait, when we move to delta -1, that is when we move to 3, we can get any number within the range of 0 to 5, because 5 is 2 apart from 3, and these are 1 apart, so we can spare another additional operation. Which means in terms of difference, it's -1 to -3 to 2. And we can draw all of these points. Now let's say we had exactly 4. Alright, so it should be clear that we can get any delta from -3 to 3. Because if it were, oh right, hang on. That would be any value from 0 to 6. And the corresponding delta would be, corresponding difference from 4 and 3 would be 0, -3 to 3, because like this is 0 apart, so it only depends on how far apart this is, and the maximum far apart we can be is 3, so it's just 3 away. At most 3 away. So we can draw all of these points in the range of 3. And you can show, like, on this side it's going to be just the reverse of this. Essentially, like, it's going to be this, but rotated 180 degrees. So I'll show you what that looks like. Essentially here, 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 and here. No, wait, sorry, that was wrong. It should only be down to here. So this is the set of all possible points we can have. Note that all of them are integers because we have an integer number of letters. If we had half of a b, that would be really weird. So let's draw a shape. Any value, any possible like delta within the range of, like, these are all relative to 4 and 3. That's why I center it. Or you can also say it's centered at 4 and 3, and then all these values around it are just close to it. So we can draw this shape. Kind of comes out to a weird hexagon. And because like we picked 3 arbitrarily, so it doesn't really matter what this size is. It's always going to form a hexagon that looks like this. And because we also we chose 4, 3 arbitrarily, so it doesn't matter. It doesn't matter the size. It's still going to look like a hexagon, and it doesn't matter where we're at. It's still going to be the exact same shape. So all of the shapes we're going to have from all of these, like the intervals that we create, are going to look exactly like this. And remember, these shapes represent the set of all possible points such that we can be at most 3 distance away from these. So, much like the interval problem, we're now going to find the intersection of the shapes like these. That sounds fun, right? Geometry. And this problem is kind of crazy because, if at first glance it's a string problem, you're creating some metrics of distance between strings. And then you completely abstract out the string problem. And then you introduce binary search. And then it becomes a geometry problem of polygon intersection. And that's, I don't know, it's kind of crazy in my opinion. It's nice that you can, totally just change it with a few observations. Yeah. So, polygon intersection is not easy. You can leverage the fact that all of the shapes are the exact same by keeping track of these bounds. Yeah, I know the editorial solution is this, and I've also consulted with some people, but I have not managed to implement this myself. So, I mean, you can try it, but I don't know, just have fun with it, essentially. It doesn't seem like it's going to be fun to write the code for. But that's the essential idea. Get rid of the string part, then do binary search, then... Oh, and of course, it's only possible when there's at least one point that's in all of the intersections. And then you can use that point as long as it's not a negative number of letters to essentially be the answer. And you can always show that, if there's some point, if there's a valid point, then there's one that isn't negative, because, all of the coordinates are positive in the first place. So that's going to be fine. Then once you do that, you use that to check, then you just print the final answer. After you implement the geometry thing, that part should be easy. So, yeah, that's about it. You do all this work, and then it comes out to an ugly implementation, then you have to do that too. This was a 2600 difficulty, which means I think that's rightful for it. Yeah. So that is about it. That's all I have. These are the solutions to the Div2 problems. I hope they were understandable. If not, you can just ask in the comments or something. Whatever you want. And that is it. Goodbye, everyone.